Welcome to GeekDIYMechanic Mechanic. The purpose of this video is to discuss the voltage drop test. From the home page, let us navigate to Knowledge, Electronics, Testing Concepts. As a prerequisite, it is suggested that you have read and have studied the following: Physics Classroom. It discusses electronic concepts and terms, Big Bad Tech, and especially the basic Kirchhoff voltage law. Please consider this video as a very high-level explanation to the voltage drop test. This video is intended to be supplemental to the reading materials provided in the resource section of this website. Before demonstrating a voltage drop test, let us discuss what this test is looking for. To allow us to understand what this test is checking for, we need to understand what deteriorates a circuit over time. Let's click on the Flow is Good button. The leftmost image depicts a healthy wire where there is no obstructions preventing electron flow. The middle image demonstrates corrosion on the inside of the insulation. This can happen if insulation is compromised and the wire is exposed to the atmosphere. For example, by poking through wire insulation, the wire is now exposed to the environment. The corrosion either impedes electron flow or actually breaks down the wire, reducing available pathways for the electrons to flow. The rightmost image demonstrates a wire that has been physically compromised either by corrosion, deteriorating the wire physically, or the wire being either cut or torn. Obviously, this reduces the available pathways for the electrons to flow. For example, heat and vibration can do this. A wire resting against the EGR, burning through the insulation, or let's say as the engine vibrates, a wire's against the head or a block and it slowly wears against the insulation, getting to the wire and wearing that away. That actually happened to me on one of my cars. Let's see what corrosion looks like. Let's navigate to the corrosion appearance. The left image shows two brass wires. The left wire is nice and clean and highly conductive, whereas the right wire is suffering from oxidation, limiting electron flow. This is because electrons actually flow on the outside of the wire strand. The right image shows what can happen to a wire if the insulation has been compromised, allowing oxidation to occur from the inside out. In this case, it was so bad it actually ate away some of the conductor. The lower left is an image of a battery terminal with a high degree of corrosive buildup. So although it looks like it's only here, it's actually on the inside of here as well. The terminal is right here, and that's the connector. In this case it's green, so it's probably the ground wire. The lower right is an image showing a terminal within a connector with a great deal of corrosion on it. Again, would affect electron flow. And these sort of issues, actually these two right here, are hard to find, because who would think to take apart all your connectors, and you're afraid to do it because you may break them, but yet in one of them could be the corrosion affecting your circuit. As you can see, corrosion can be very obvious, like the battery terminal, and unfortunately very stealthy to detect, illustrated by the corroded out wire from the inside out, like up here, or even the connector, like I was saying. Let's navigate to voltage drop test goals to learn how we can leverage a digital voltmeter or scope meter to uncover corrosion or locate a compromised conductor. For us to maximize the voltage drop test, we first need a high-level understanding of how the voltmeter works, Kirchhoff's voltage law, how corrosion affects the circuit. Let's start off by discussing how a voltmeter works. A voltmeter displays the difference between two voltage potential points in a circuit. Due to the DVM, digital voltmeter, having high internal voltage sensing resistance, usually 10 mega ohms, and automobile circuits tending to be of much lower resistance, meaning the high resistance won't affect, in this case the high resistance won't rob anything from the circuit. The voltage sensing portion, like the voltmeter or what's inside the PCM, draws very little current. The red probe is usually attached to the higher potential point in a circuit, and the black probe is usually attached to the lower potential point in a circuit. Let's review the following table to take the concept home. The first entry is an example of the DVM being connected between the positive and negative leads of a typical car battery. So this would be the positive post, and this would be, let's say, ground or the negative post. And since the potential difference between them is 12, the voltmeter will show 12. The second entry would be if the test leads were reversed. So you literally just take the leads and flip them. You'd get negative 12. The third example is an example of placing the red probe on battery positive and the black probe on any 5-volt reference, resulting in a potential difference of 7 volts. To learn more about voltage sensing, how voltage sensing works, I suggest visiting the All About Circuits website. Clicking on the Learn More link will take you to this website, allowing you to get into more detail. The next concept to have a high-level understanding of is Kirchhoff's law. This is often referred to as KLV and can even be used as a verb. Let's calculate the KLV. What is the KLV? For a more detailed explanation of this law, I suggest watching Jim Pytel's training video, which you can access right here via this link. But for our purposes, this law means that all the voltage will be used up by the expected load of a circuit. For example, if we are diagnosing the circuit providing high voltage to the starter would be considered the expected load of that circuit, as illustrated in this little diagram here. Of course, it is possible for a circuit to have multiple loads in it. Example, interior lighting. But for this discussion, let's keep it simple and just imagine a circuit having one primary load, a starter in this case. Kirchhoff's voltage law states this expected load, the starter, will consume all of the available voltage. Therefore, if we find any substantial voltage anywhere else in this circuit, we have found a problem, which tends to be caused by corrosion. This additional voltage is what the voltage drop test is trying to find. A healthy circuit will result in no additional voltage drop detected outside of the expected load for that circuit. Once you understand the concepts of the voltage drop test, and with experience, you will be able to apply this test to more complicated circuits. Let's discuss how corrosion can affect circuits. The simple circuit with no corrosion panel depicts a good circuit with good wiring. The load has all the voltage to itself. So measuring from B to D, you get 12 volts, which makes sense. The load should have consumed, because of KLV, all the voltage of the circuit. A to B should be 0. Remember, this is at 12 volts, that's at 12 volts. C and D would be 0. Why? Because this is 0, 0. 0 minus 0 is 0. 12 minus 12 is 12. But since B is 12, D should be 0. You get a voltage drop of 12 volts. Again, this is a healthy circuit. This is what we expect when we look at this schematic or we're working on the car. We expect the load to get full voltage. And the voltage drop tells you how much voltage that load is consuming. The how corrosion affects circuits panel depicts how having corrosion added to a circuit robs voltage from the primary load. This is the principle highlighted by Kirchhoff's voltage law. All the loads will share in utilizing all the voltage. So when the voltage drop isn't what you expect it to be for your expected load, you know it has to be somewhere. Using this fact, you can track down what is consuming it via simple voltage drop tests. Looking at this diagram, you will notice that the expected load has only a voltage drop of 10. We expect 12. Remember, the circuit looks like this, but yet we have an issue that we can't find, but we know it's there because we have 10 right here. So where did the 2 volts go? The resistance between points D and E represent corrosion in a circuit. Remember, corrosion can be very difficult to visually find, but its effect on a circuit is very easy to find. Again, due to this corrosion, the expected load is only receiving 10 volts. Let's say that load is a fuel pump. I'm sure it's fair to say that it will not do as much work with this lower voltage. This means this corrosion could cause lower fuel pressure. Just for review, let's leverage the Java circuit simulator to review what voltage drop is and how current affects it. Let's click on the voltage drop review button. The main purpose of this circuit is to refresh what you have learned about Ohm's law. Using Ohm's law, you can calculate the voltage drop across the load. Just to keep things simple, this circuit will have just one load to make it easier to see voltage drop in action. As you can see, when current is flowing across the single load, and it is right now, because you can see the little electrons flowing in a circle, all the voltage is consumed by that load, making both voltage test points on both sides of that load have maximum potential difference. In this case, all 12 volts are consumed. Remember the principles of KLV? So we have 12 volts here, 12 volts is here, it's consumed by the load, therefore we should have 0, and we do. Since 0 is here, 12 is here, the potential difference measured by the voltmeter is 12. 12 minus 0 is 12. Now, let's see what happens when we open the ground side switch, called ground side, since the switch is after the load. Load is after, thus ground side switch. Since there's no current flow, notice that the voltage stays constant all the way to the switch. So from the positive point of the battery, goes all the way across to this test point, across the load with no voltage drop because no current is flowing, all the way to the open in the circuit. The potential difference across the load is 0 since both sides of the load are at 12 volt. That's easy to see. Green, green, 12, 12, and 0. It reads 0 because 12 minus 12 is 0. So, because of this, the single load will not exhibit a voltage drop. Again, current must be flowing for a load to consume its fair share of the voltage. In this circuit, all the voltage will be consumed by a single load. Again, we have one load, 3K. Again, closing the ground side switch will allow current to flow. When current flows, voltage drop occurs. Therefore, to perform a voltage drop test, current must be flowing. Now I feel we're ready to use the Java circuit simulator to see the voltage drop test in action. Let's click on the voltage drop test button. Let me start by explaining the circuit. Let me remove all the probe wires to show the circuit we are testing. Now that the probes are removed, let me move these two just so it's more clear. Now that the probes are removed, you can see there are both power side and ground side switches. Power side switch, ground side switch. Ground side because it's after the load, power side because it's before the load. You will notice 12 volt power source and a 5K load. Let's place the DVM test probes at strategic places on this circuit to start a voltage drop test. I'll do that by just reloading this circuit. First thing to remember is current current must be flowing for voltage drop to occur. Therefore, to conduct the voltage drop test successfully, current must be flowing. What does that mean? The circuit must be on. For example, if we were testing the high power portion of the starting circuit, the ignition key must be to the start position, which closes the circuit, sending power to the starter. You can see the values for each test point by looking at the scope readouts at the bottom of the screen. So test point 1 is here, test point 2 is here, and test point 3 is here. With current flowing, both test points in test point 1 are at 12 volts. 12 volts there, 12 volts there, because it's on the same side of the load. Therefore, since 12, test point 1 should read 0, and it does, because 12 minus 12 is 0. Likewise, test point 2 reads 0 since both points are at 0. This is test point 2. We're on the ground side of the load. There's 0 here, 0 here. 0 minus 0 is 0, and that's what test point 2 displays. On the other hand, test point 3 is across the load, creating a voltage potential difference. In this case, the scope reads 12 volts. This means that this load consumed all of the 12 volts, which is what we would expect due to Kirchhoff's voltage law. Nothing else is robbing any current or voltage. This is what we expect as the result of the voltage drop test on a healthy circuit. Before seeing how corrosion can affect a circuit, let's just play around and see why current must be flowing to perform a voltage drop test. I know I'm harping on this current flow, but this is the most common mistake when executing this test. So bear with me. Hopefully you'll remember that. Let's start by flipping the power side switch. What do we notice? Test points 2 and 3 go to 0 because it's after the open. In regards to the voltage drop test, test point 2 looks okay. We expect no voltage drop on this side and we get 0. Looking good. But test point 3 going to 0 implies that the load is not consuming any voltage or current. Right? Kirchhoff's law said there should be a voltage drop here. Performing the voltage drop test improperly could have us think the load has an internal open. Obviously, this is not the case. Therefore, current must be flowing. Let's see what happens when the ground side switch is flipped. Test point 1 looks okay since it is very close to 0. Again, there's 12 here, 12 here, 12 minus 12 is 0. That's what we'd expect. But test points 2 and 3 do not look correct. Test point 3 does not show a voltage drop. Test point 2 has a huge voltage drop of 12 volts. This would imply huge resistance, which it does. It has infinite resistance in the form of an open circuit. Again, for the voltage drop test to produce proper results, the circuit must have current flowing. Sorry for discussing current flow numerous times, but like I said, this is the most common mistake in the voltage drop test, not having current flowing. So let's close all the switches and review what a healthy circuit looks like again. With the switches closed, this is a healthy circuit flowing current. You expect nearly all of the voltage to be displayed at test point 3 across the load. In an actual automobile circuit, test points 1 and 2 should read about 0.2 volts or 200 millivolts or less for low current circuits, example like sensors, and up to 0.6 volts or 600 millivolts or less on high current circuits, like a starter circuit. I'm going to add resistance representing corrosion in a circuit on the power side of the circuit. Wow. Even just adding a resistance of 100 ohms allows you to detect this corrosion via a simple voltage drop test. Both test points 1 and 3 have changed. Test point 1 now reads outside or acceptable range for low current circuits. It is greater than 200 millivolts. It's actually 235.29 millivolts. In addition, the load does not receive all of the voltage. It has just dropped to 11.76 volts. Obviously, as corrosion gets worse, it will rob more and more of the voltage from the load. For the heck of it, let's flip the ground side switch. Stopping current. Let's pause for a second and let the scope settle. Notice how we are now fooled by the reading at test point 1. It reads 0. Yet we know there's an inappropriate voltage drop in this leg of the circuit. Again, current must be flowing for voltage drop test to function correctly. Let's add corrosion in the form of resistance to the low side of the circuit and see what we notice. Well, we see that test point 2 is now reading an unacceptable value of greater than 200 millivolts. In addition, the load is not receiving all of the voltage. It is dropping / consuming 11.76 volts. Well, there you have it. I hope my high-level explanation and the use of the Java Circuit Simulator allowed you to understand how to properly perform and interpret the results of a voltage drop test. Some of you, especially with an electronic background, might think using a continuity tester or a continuity test might be better or easier. Unfortunately, since automobile circuits are usually over an amp of current flow, continuity tests are not beneficial. This is because when a meter performs a continuity test, it does so by playing a very low voltage and low current. So, In a wire where every strand except one strand was destroyed, picture that in your mind. Big thick wire, but all of them got rubbed away except for one strand, would show low resistance, because it's low voltage and low current, looking acceptable, yet could not allow high current to flow, being actually unacceptable. Once you understand and know how to properly execute the voltage drop test, you will see that this is an extremely powerful and valuable test. I hope this video will allow you to add this test to your test suite. Thank you for watching. I hope you found the information helpful.